Okay, now that you've watched the Tyler DeWitt video on what a galvanic cell or voltaic cell, and I actually refer to it as voltaic cell as well, we're going to start talking about the math that's involved with it. And the reason I had you watch his video, he does such a wonderful job and he has such great visuals that I thought that would be 100% better than what I could have done here at home. You know, in my classroom, I could have drawn things on the board for you, and I would have actually had a demo going for you, but he had those visuals, and he's just awesome. And so I would highly recommend any of his videos, of anything you don't quite understand. So anyway, start out with a joke. So why did the galvanic cell need a lawyer? And it was charged with assault and battery. So hopefully you've watched that video and you understand the salt bridge and battery going on. So we are going to talk about a voltaic cell. And so a voltaic cell is a chemical reaction that actually produces electricity. And so you get a positive voltage in a voltaic cell, a positive voltage. And a positive voltage means the reaction is spontaneous in the direction at which it's written. Okay, so I do want to, because we talked about spontaneity with the last unit in thermochemistry. So spontaneous is a positive voltage in the direction that the reaction is written. Next week we're going to talk about an electrolytic cell. An electrolytic cell is when we have a negative voltage. So we'll talk about that next week. So voltaic cells produce electricity, so we get a positive voltage if we want a spontaneous reaction. So with that in mind, I want to start us off by looking at a chart. And so this is what's called the reduction potential chart. And I have uploaded this on Moodle, so you can print this out or look along with me. So if you'll notice that we've got voltages at the over onto the side. These are all written as half reactions, and so you're seeing those electrons involved. And if you'll notice, the electrons are all on the reactant side. So these are all reductions. Every one of these is a reduction. It's almost like a most likely to succeed, but most likely to succeed in being reduced. So the more positive the voltage, the more likely it is to be reduced. As we go down the chart, you're going to see a negative voltage, and so these are not likely to be reduced. Not likely to be reduced. So, and these numbers have all been based on hydrogen. Basically, they tested all these either elements or ions versus hydrogen in an electrolytic cell, in a galvanic cell. And if you'll notice in the chart, 0 here, the hydrogen ion is set at 0. So that was the standard. Everything got tested against hydrogen. And so you can see the fluorine gas is more likely to be reduced. So we're going to be using these voltages, so we're going to be looking at certain ones. And so this is where the math comes in. So I do want you to know that this is a reduction potential. They did not make an oxidation potential chart, and the reason they didn't make an oxidation potential chart, if they did, it would be the exact, actually like the mirror image of this. This chart would be flipped around, so these would all be on the reactant side, this would all be on the product side, and if you flip it around, all the signs change. So we'll talk more about this next week. But I'm just going to introduce it right now. So if I flip this reaction around here, this would be a negative 2.87. So the fluoride ion doesn't really like to be oxidized because it would be negative. But if we go down, the potassium solid does like to become an ion, so this would have been a positive, which is what makes potassium so reactive. And if you remember in Chem 1, the activity series, this is the activity series This is the activity series that you learned in Chem, talked about in Chem 1 for single replacement reactions, whether or not the reaction would take place or not. It just didn't have the voltages or the electrons that I'd see. The same chart. All right, so this is the chart I'm going to be referring to in the problems. So let's go ahead and go into our examples. And so I've uploaded this as well. And so our first example I start out with is the reaction that Tyler does on his video. And so we've got that piece of zinc in the zinc solution and the piece of copper in the copper solution. I would always want you to put can't just have ions, you got to have some sort of solution. And it's always some sort of nitrate solution is a good solution there, because nitrate likes to be a spectator. So even though it's a spectator, it needs to be present in the solution. You can't just get copper ions. Didn't have to be nitrate, but nitrate's a good choice there. So first thing I'm going to do is find these two things in our chart. And so if I go and look at our chart, I'm going to be looking for the copper 2 ions and the zinc ions. And so if I find there's a copper 2 plus 2 electrons makes copper solid, I get a positive 0.34 volts. So I'm going to use that one. And so there's one. And notice I've got to always be careful with copper, because there's copper 1 going to copper solid, there's copper 2 going to copper 1. So you have to be careful with copper. I would pull down on this chart more, and then I will find zinc. Zinc's much further down. It's a 2 plus 2 electrons making zinc solid. Notice that it's a negative 0.76. So what I'm going to do is figure out how to make a positive voltage with this. So I'm going to go back to that original chart that I had, and I'm just going to write those two reactions up here. So we have copper 2 ions, which is aqueous. I will tell you, I think Chem 101 requires that AQ for those ions, plus 2 electrons. That makes copper solid. All right, and that was I'm going to write it here, that was a 0.34 volts. And then we had the zinc 2 plus aqueous plus 2 electrons is going to make zinc solid. And that was a negative 0.76 volts. I like to look at them this way for you can see. So I'm going to get ready and do my half reactions, my balance, my cell notation, etc. But my electrons can't be on the same side. I'd have to have one thing that's being reduced and another thing that's being oxidized. And so I want to flip one of these, and you want to flip it so that you get a positive spontaneous reaction. So I want to flip it, because if I flip it, I'm going to end up changing the sign. So hopefully you can see this one's more likely to be reduced because it's a more positive value. So this one's going to stay reduced. I'm going to go ahead and leave that one as my half reaction. So Cu2 plus aqueous plus 2 electrons yields copper solid. And I'm going to go ahead and write the voltage there. And the other one I'm going to flip around. And the reason I'm going to flip around, again, my electrons can't be on the same side, but it's not going to get reduced, it's going to get oxidized. So this one's going to start out with zinc solid, and it's going to make zinc ions, and it's going to give 2 electrons. That's AQ. I may sometimes forget to write IQ. And this was, now that I flip it, is going to be a positive 76 voltage. Let me go ahead and put positive on both of those. All right, so just like we did on the balancing, we're going to now combine these two equations. And so you got 2 electrons and 2 electrons for the balanced net ionic reaction. Those are going to cancel each other out, and now we're just going to bring everything else down. So you get copper 2 ions plus zinc solid is going to make zinc ions plus copper solid. Okay, so there's my balanced. So let's identify what's going on in this reaction. So this reaction here, because our electrons we're going to from a 2 plus to a 0. So you can see that it's going down in number, but also if the electrons are on the reactant side, this is being reduced. So we've got reduction here. All right, and so on this one, we've got our electrons over on the product side going from a 0 to this is oxidation. So once you identify that, then you can figure out which is your anode and which is your cathode. Your anode is always where oxidation occurs. So this is your anode. And reduction is called your cathode. Okay, so there's a couple ways you can remember this. Most students remember, and this will help when we do lab, red cat. So the reduction is the cathode, and then an-ox. So the anode is oxidation. Red cat and an-ox. I remember that the consonants go together and the vowels go together, whichever. Okay. The reason that's important, so because I'm going to label this, and so this one, the copper, is the cathode. So we got the cathode over here, and this is the anode here. So because I just figured that out. The reason that's important is because electrons always go from the anode to the cathode, alphabetical order, anode to cathode. So the electrons are going to leave this side, travel through the wire, going to go through that voltmeter, register a voltage, and then they're going to end up coming over here, which is why this side becomes getting real negative and we're losing the charge over here. So again, Tyler does an excellent job of what that salt bridge is to help balance out that charge. All right, we'll deal with that salt bridge in just a second. So the reason that's important, when you do the cell notation, it's always the anodes first and then the cathodes second. And so for our anode was the zinc, and so it's always the reactant. So Zn, solid, and then you put a line, and then you put the product. The electrons don't show up. Okay, so there's the anode, and then you put a double line, which is showing that separation, and then you do the cathode, reactant, and then product. So then Cu2 plus aqueous / Cu, solid. All right, that's the cell notation. Coming from here, you take it from there. Sometimes students find it easier to find it in the half reaction. All right, so what is the E stands for electromotive force, which is basically the force of the electrons coming through, and it's measured in volts. They put it E of the cell. It's electromotive force is what it is, and it's measured in volts or voltage. So the E for the reaction is simply, now that I got these in the correct order, is those added together. So I just add those together and I get a 1.10 volts. This is positive. You could add them together and they get negative, okay? But positive means it's spontaneous. Spontaneous means this reaction is actually going to go the way I say it's going. It's going this direction. If I get a negative, that means it's not going that direction, it's going the other direction. If it goes through the meter negative, that means it's, and unfortunately we don't get to do the lab, but if you was going through the voltmeter the wrong direction, you would know that you have your wires switched. Okay. So I've answered those questions. It says label the anode and cathode in the diagram. Well, I just did that, the anode and cathode. Identify the direction of the flow, and I did that with my electrons, you see, so it is flowing from the left to the right. But I'm going to write something here for you can always know. It's always going to go from the anode to the cathode. Because the way ours is drawn, this is the anode and cathode. And I typically will write anode on the left and cathode on the right because I think left, right, but they're not always, and that's why I've got a couple of examples. So in this particular container, we are going that direction, from the left container to the right container. So it will always go anode to cathode. Always, always, always go anode to cathode. Okay, I'm going to skip forward for just a second and go down to number 5. It says label each electrode as positive and negative. And this is sheer labeling. It really has nothing to do with anything. It's the way we label a battery. It really doesn't mean, well, it does, but so the anode gets this is black, but normally I would label it on this piece of metal. Gets a negative label, and the cathode gets a positive label. Okay, positive label. That's just a labeling. Doesn't mean it's positive or negative. The negative means this is the source of the electrons, and the electrons are leaving the anode and going over to the cathode. So this is, and the negative charge is being built up over here, but this is just sheer labeling. So on your battery, you have a positive side and a negative side on your battery. The electrons are leaving the negative, going to the positive. That's the way the electrons are flowing, and that's just a sheer labeling. Anode negative, cathode positive. You can remember that because the cathode has a T in it. Okay. All right, let's go to the salt bridge. So on the video, Tyler did put a actual NaCl in his salt bridge, and so he had sodium chloride. Write it over here. Sodium chloride has, and sodium chloride is not a great salt always, and we'll look at that in a moment. But you really want some sort of alkali metal and an anion that's not doesn't precipitate very well. So we'll use this one for this because that's what he used in his example, but we'll look at a couple of others in a moment that we might not want to use that. All right, so there's mine. So you has a positive and a negative, has a cation and an anion part to our salt bridge. That's what's in that. And again, it is a solution with cotton balls, and it seeps out is what it does. Okay, so because these electrons are flowing over here and we are losing these copper 2 ions are getting accumulating on there. Those copper ions are accumulating on there. I should say copper solid is accumulating. We're losing those copper 2 ions going on. And because that negative is moving over here, I was going to switch to yellow. The sodium ions, the sodium cations, are actually going to flow towards the cathode. So the positive goes towards the cathode and the negative goes towards the anode. The negative goes, and that is surely to balance out the charge. It allows the reaction to go longer. That's what the salt bridge purpose is. Okay, so it says identify the direction in which the cations are moving. They are moving towards the cathode. And in this case, that would be the copper beaker. Okay. Hopefully this is making a little sense. I already answered number 5. Okay. And number 6, and again, Tyler does a great job. Which electrode is increasing in mass? Well, these copper, you can look at your balanced equation. Let's see if I can highlight it for you can see it a little bit better. It's in the middle of a mess here. So hopefully you can see what solid is forming there. What solid is forming? Well, the copper is forming, and so the copper is accumulating onto that, and so it is the cathode. So the electrode, the cathode, is always going to be what's gaining the mass, and so cathode is always going to be gaining the mass, and so for this case that is the copper solid is what's going to be happening. And which is decreasing? Well, look, it's zinc solid is going to zinc aqueous. So the anode is always losing the mass. And so in this case, that would be the zinc solid is being lost. And that will be an always. So cathode is always going to gain. So once you identify anode and cathode, a lot of these questions can be answered. All right, let's look at the next 2 questions. Alrighty. So it says which ion concentration will decrease. So if I go back, I'm going to go back 2 of them. Can you see that the copper ion is, because it's going to copper solid, we're going to be losing copper ions, but yet my zinc, it's actually the one that's decreasing, the zinc metal, and it's going into ions. So zinc ion, look here on the balanced equation, the zinc ion is forming, but the copper ion is disappearing. So let's go back to that question. All right, I'm on question number 8. So which ion will increase in concentration? That is going to be the zinc ions. And you'll notice it's opposite. Which ion will decrease? And that will be the copper ion. And you can look at your balanced equation and figure that out. All right, now we got some stoichiometry to do. It says if one electrode loses mass, now remember the one that's losing the mass is the anode, and the one that's gaining the mass is the cathode. So it says if one electrode loses a mass of 0.3 grams, how much will the other gain? Well, a lot of students go, oh, law of conservation of mass is 0.3 of 0.3. No, unfortunately, not exactly like that. I'm going to get my balanced equation back up here for we could see. Cu2 plus aqueous and zinc solid, and we're getting zinc ions. Lost something there. And zinc's, that's really ugly. Let's fix that. Aqueous, and we're getting copper solid. Okay, so the anode, which was the zinc, right? The zinc. So we're going to start out with, let me go further down here. We're going to start out with 0.3 grams of zinc. We're going to do a little stoichiometry. And we're going to bring grams of zinc down, and then 1 mole of zinc. Anytime grams with moles, it's 1 mole. And then this is the molar mass, and periodic tables are a little bit different on copper, but we'll go with 0.4 for zinc there. And then you have what's called that mole-mole ratio, and we are looking for the amount of copper. Now this particular reaction, for every 1 copper there is 1 zinc, so this one is a 1-to-1 ratio. They're not always a 1-to-1 ratio. Alright, so then for every 1 mole of copper, remember anytime mole and gram go together, mole gets a 1. You're going to get 63.5 grams. So this is that mass calculation that you learned in Chem 1. So this would be a 0.291 grams of copper. So close. So where's the other? Well, the other's in ion form, so you still get law of conservation of mass, but so we've got some electrons and things accounting for that. So that's that mole-mole ratio going on there. Okay, so hopefully that makes sense. We're going to do example number 2. So example number 2, we've got some gold and we've got some nickel. So again, when I get those voltages, they're going to be from the chart. So I'm actually going to write over here. Let's write it in black so we can see. We're going to do, this is coming, I thought I was writing in black, apparently I'm not. Okay, so we've got gold 3 plus 3 electrons. It's going to make some gold solid. Again, I'm doing this just to figure this out for a second, so I'm pulling from that chart first. So the chart, they're both being reduced. Okay, so if I look on the chart, and if you printed out the chart, you can see this one's at 1.5 volts, and this one's at negative 0.25 volts. Alright, so which one's more likely to be reduced? Well, the gold is more likely to be reduced, so the gold is going to be my reduction part, so I'm going to leave that. I don't have my aqueous. I'll get my aqueous in the final one. How about Oh, we'll get that. So this is going to stay, but I'm going to flip the other guy around. So we're going to get nickel, solid, making nickel ions, plus 2 electrons. Because remember, I have to have one being reduced, one being oxidized. So when I flip it around, this is now going to become a positive. I will tell you it won't matter if I flipped around, it became negative, as long as when I add them together it's a positive value. And my third example, I do that. So this one is going to flip around, become, so you don't just flip it to make it a positive, it's when you add them together. So if I add these together, hopefully you can see I get a 1.75 volts there. Okay, so now I'm going to do a balanced equation. So I want to do this one with you to show you something here. My electrons have to be the same number, which is why we went over balancing equations. Okay, so I need a number so that 3 and 2 will both cancel out. So I need them both to be 6. Now I need you to watch this because this is important. So I need to multiply the top by 2. So this is 2, this is 6, this is 2. Notice, I don't change the voltage. Okay, voltage is what we call an intensive property, and so it's not going to change when we change that coefficient. Okay, so unlike enthalpy and entropy and Gibbs and all that other, I did change these numbers. If I flip it, I change the sign. Do not change the voltage. Do not change the voltage. Okay, this one needs to be multiplied by 3. 3, 6, don't change. That's why I went ahead and wrote that. Okay, so now can you see that your electrons are going to cancel out? If they don't, you've messed up. Okay, and now I'm going to write them. So now we've got 2 gold, whoops, oh, just messing up like crazy now. 3 gold ions, aqueous, plus, 2 gold, 3 ions, plus 2 nickel solids, going to yield us 2 gold solids, plus 3 nickel 2 ions, aqueous. There's my balanced equation. Alright, what's happening here? Well, this is the reduction, right? That's your reduction, so this is your cathode. Remember red cat, that's your cathode. And this is oxidation, so this is your anode. Why do we need to know anode and cathode? Because that's going to tell us lots of information down there. So I'm going to label, so we got nickel. Nickel's here is our anode. And this is our cathode. Okay, so anode, cathode. So with that, I'm going to go ahead and do several things. Anode gets a negative charge. Cathode gets a positive charge. Electrons flow from the anode to the cathode. That's the direction, always alphabetical order, anode to cathode. So my electrons aren't going that direction, my electrons are going that direction. All right. So with that, this cell notation, we start with the anode first. So we would have 3 nickel. And I will tell you, some books don't put the coefficients, they just put the symbols. I'm going to go ahead and put the coefficients since they're in there. Okay, so 3 nickels. We're going to make 3 nickel ions. Then we have the showing that they're being divided here. And then you're going to end up with 2 gold ions, that's the reactant, yield, that's like your yield sign, 2 gold solids. All right. So it says label the anode, cathode, check. Identify the flow of the electrons. The flow of the electrons are always the anode to the cathode. Anode to the cathode. So in this case, they're going this direction, right? So they are going from the nickel side to the gold side, because this is gaining the electrons. Identify the direction of the salt bridge. All right, for this one we'll still use sodium chloride. All right, the cation, which is the sodium, is going to always go towards the cathode. Cation always goes towards the cathode, so that is going to go that direction this time. The anion part, the negative part, goes to the anode. That's what happens in the salt bridge. So cathode. So this one's going towards the gold container. So it's going to go towards the gold beaker to balance out the charge. Label each as positive or negative. Done that up there. Which electrode is going to be losing or increasing in mass? Remember that the electrode that always increases in mass is always the cathode. I'm putting those words for you. And so which one's the cathode? That is the gold solid. Again, look at your balanced equation. You can see gold's forming. So your next question, which didn't show up, it's on the next page, is going to be which one's going to decrease in mass, and that is going to be the nickel. Decrease in mass, so this one was gold, because this was the cathode. This is going to be the nickel solid. It's the anode. Which ion is going to increase? Well, it's going to be the nickel ion. And which one is going to be the gold ion. All right, now we got some stoichiometry to do. All right, for some reason I lost recording a second ago, but we're back. All right, so we're going to do the stoichiometry, and so the loss again is the anode, and the one that's gaining is the cathode. Make sure you always read the question because it may be going the other direction. All right, so we know that the anode was nickel, so we've got 0.2 grams of nickel, and we're going to figure out how much gold. So let us begin. So we're going to bring grams of nickel to 1 mole of nickel. The molar mass is 58.7 from the periodic table. And now we're going to do that mole-mole ratio from mole of nickel to mole of gold. And we're going to find that from our balanced equation. And nickel has a 3 and gold has a 2. And we're going to take it all the way to grams. For every 1 mole of gold, there are 197 grams. Again, just a mass stoichiometry problem. And so we would find that we would get 0.447 grams of gold.